Okay, so we're continuing now section 13.2, and we learned about line integrals with respect to arc length. But we can also have line integrals with respect to variable x or variable y. And those are given by the formulas on the highlighted parts below. So, you might be thinking, oh, wow, this is more formulas. But these formulas are actually come from the formula, the one with respect to arc length, the line integral with respect to arc length. Let me show you how. Okay, let me show you how. All right, actually, I kind of, let's see here. Okay, I really like what I have written here, but I am going to have to remove it because I got to write something new. But think about, this part here. All right, so let me go ahead and clear this. All right, so let's say that let's say that your arc, that this is your arc, okay? And hold on here, I gotta adjust the mouse here. So this is, hold on one moment. I know what to do. There we go. Okay, that's fine. Okay, so let's say that this is your arc, and this is delta S. Well, note here, in this case, for this arc, okay, delta S is equal to delta X. Delta S equals delta X. And delta Y equals 0. There's no triangle here. Okay, there's no triangle here. The arc is just a horizontal line segment. So delta S equals delta X, but delta Y equals 0. Now, remember that delta S was approximately equal to delta X over delta T squared plus delta Y over delta T squared times delta T. But if delta Y equals 0, then this part here, delta Y is 0. So that's going to give you just delta X over delta T squared dt. Okay, so delta S is approximately equal to delta X over delta T, that quantity squared, times delta T. But that's going to equal just delta X over delta T times delta T, and that's going to give you delta X. So as n goes to infinity, meaning the space curve C, you break it up into more and more little arcs, ds will equal dx. ds will equal dx. And also, I'll note that x prime of t is equal to dx dt. So x prime of t times dt will equal dx. Okay, so this is going to be important here, and this result here is going to be important. So when we go, let's see, now when we go to those formulas, they should make sense. Let me just see here, hold on. Okay, so if we are doing a line integral with respect to x, then ds equals dx. So in formula 7 there, we replace ds with dx, but that means then that of course dx is equal to x prime t dt. So the line integral with respect to arc length can be if the arc is a horizontal line segment with no curvature, a horizontal line segment, because the arc is equal, you know, the ds equals dx, the line integral with respect to arc length is then equal to the line integral with respect to x. And hence you get that first formula there that you see in formula 7. The second formula you see in formula 7 is with respect to, it's the line integral with respect to the variable y. So these are two that you're going to need to know. Now, sometimes what happens, well, a lot of times what happens is we want to do this. Okay, we want to add a line integral with respect to x plus a line integral with respect to y. Okay, take a look at that for a moment. One moment. Okay, just give me one moment. Okay, all right, so this is really, let me just show you this here. So, I mean, here you have an integral, okay, over along some curve C. And it looks like, you know, this looks like, well, how can this be? Either it's an integral with respect to x or an integral with respect to y. And I see a dx here and a dy here. How can that be? But this is notation for the sum of two line integrals. The first line integral is a line integral with respect to x along that space curve C plus another line integral along that space curve C with respect to y. There are reasons for using this notation, and so you're going to have to get used to it. Now, of course, what's going to be required is parameterization of your space curve for these kind of problems. And what I'd like to do is when we return on Thursday, I'm going to do an example in the book where you are actually doing the sum of two line integrals. The sum of two. I want to say it right. Yeah, the sum of two line integrals, one with respect to x and one with respect to y. But I don't think we have enough time to do an example tonight. So on that note, I think I will hold on here. Let me go ahead. Well, are there any questions before I stop this recording? I'll mention one quick thing. I can actually fit one quick thing in here. I can fit one quick thing in here. That's going to be useful. So many times you want to parameterize a line segment. And there is a formula that always works. It's for a line segment. If the line segment starts at the point r sub 0 and ends at the point r sub 1, those two vector points, you can parameterize that line segment with the vector function r of t equals 1 minus t times r0 plus t times r1, where t goes from 0 to 1. It works for any line segment with a starting point at r sub 0 and an ending point at r sub 1. Okay, not hard to prove, but that's a formula you'll be wanting to use. Okay, let me go ahead and stop the recording there. Very good.